Okay. Hello, everyone. In this week's Q&A seminar, we host Ho-Tat Lam from Stanford. He's going to talk about vertex tube algebras. If you are ready, Ho-Tat, you can just take away.
Yeah, thanks. So thanks for the invitations. So today I'm going to tell. Yeah, I decided to change the title a little bit in the end because we were actually debating what's the correct name to use. So you can call it either vertex tube algebras or chiral tube algebras. Depends on your physicists or mathematicians. I'll explain the sort of the connections between the two. And then I also have a subtitle. The subtitle is really summarizes the motivations of this work. It's really trying to understand chiral algebras, which is a very gigantic mathematical objects sitting inside 2D CFTs, and another important concept, topological defects. Okay, and this is work done in collaborations with Nathan Benjamin and Conghuan Luo, and they are both from USC, where I'm going to start as a faculty job. So these are my future colleagues, and then we are already writing papers together. Good. And the paper is a work in progress, and hopefully will appear this year. Yeah, I guess I have a very short time to finish the paper. Okay, good. So as I already mentioned, the motivation of this work is really trying to understand two very important concepts of symmetries. So I hear already. I saw on the YouTube that in this seminars, a lot of people already talk about non-invertible symmetries, topological defects. So I'll just say very briefly. So one very important concept of symmetries or generalizations of symmetries is what's called topological defects. So they are essentially a modern incarnations or modern generalizations of the symmetries that we're used to. But then, very importantly, in 2D CFTs, there's also a very important concept of symmetries coming from chiral algebras. So chiral algebras represented infinite continuous symmetries. So it's a very gigantic and large symmetries. So the questions that we were trying to answer or we're trying to understand better is that what is the interplay between these two important concepts of symmetries in 2D CFTs? So the playgrounds in this talks will be about 2D CFTs where these two objects coexist. Okay. And as we'll see that very natural symmetry structures emerges when we try to merge these two things together. And this is the things that we essentially invented or we come up with. And we call it chiral tube algebras or vertex tube algebras. Okay. So this is the sort of the overarching summaries of the talk. So now let me say a little bit what we're going to do. So because both of them are very important concepts and some of them are very old, but then may not be familiar to everyone. So the plan of the rest of the talk is that I'll spend quite a bit of time reviewing some of the concepts, and I also try to find connections between these two concepts. So in particular, I'll discuss topological defects and introduce something called tube algebras. And this is algebras that can be associated generally to topological defects. And then I'll talk about chiral algebras. And then chiral algebras in mathematically are also called what's called vertex operator algebras. So as you can see already from the name of this algebras, what we are doing is essentially merging these two concepts. So hence we have this ideas of chiral tube algebras or vertex tube algebras. And in this case, I'll introduce the concept and discuss some examples. So one of the examples will be W3 algebras and also its orbifold. And somewhat surprisingly, the structures that I'm going to mention can already be seen in Ising CFTs. And in fact, in Ising CFT, it has a pretty complicated chiral tube algebras, as I'm going to explain. Okay, so let me now begin with the review. So because I expect most of people already sort of heard about topological defects, so I'll be rather brief. But then I still want to mention some important concept about topological defects. So one line summary of topological defects is that they're essentially generalizations of global symmetries. And you can ask, why are they generalization of global symmetries? The reason is very simple. It's because their defining property is that there are some defects. It can be line defects or surface defects or even higher dimensional defects. But their defining property is that they have to commute with stress tensors. Okay, so if they commute with stress tensor, then that means that imagine that I have time evolutions. Okay, So if I insert this operators, this topological defects horizontally at some fixed time slice, because it commutes with stress tensors, so it commutes with Hamiltonians, so I can evolve it up and down without changing the correlation functions. So that's why if I insert an operator here or insert the operator at a later time, they give you the same answers. So essentially, the fact that this operators commutes with stress tensors implies that they are invariant under time evolutions, and as a result, they lead to conservation laws. And that's why we call them symmetries. That's why they're generalization of symmetries. Okay, so sort of a canonical examples of topological defects that is that we can consider topological lines in 2 dimensions. Okay, so there are some line objects in 2 dimensions. And the classic example is Ising CFTs, and this is the things that will also come back later when we discuss Chiral algebras. So in Ising CFTs, usually we think about local operators. So there are 3 set of local primaries. They are conformal primaries. So one of them is identity operators. The other is what's called a spin operators. So they're essentially the spin inside when we define the Ising models. They're essentially a spin inside Ising models. And the other operator is called thermal operators. So this is operator that if we add to the systems, it will trigger the phase transitions. So it will bring you either to a symmetry breaking phase or symmetry preserving phase. Okay. So relatedly, there's also a set of topological lines. And because Ising CFT is what's called diagonal CFT, meaning the left and right has essentially same conformal dimensions. They just pair up in a diagonal ways. So there's a set of lines called Verlinder lines. So these Verlinder lines are topological lines, and you can label them by identity operators n and eta. And the important properties of these topological lines is that you can imagine that bringing 2 topological lines in and then fuse them into a new lines. So this is what this fusion is describing. So it's saying that if I bring a line A and B together, they can give you a different topological lines. Okay. So for example, if I bring eta and eta in, it will give you identities. And then this essentially is a property that this is describing as Z2 symmetries because I'm applying the symmetry twice. It just recovered the identity. So you just undo the symmetries. So that's why this eta line is essentially describing the Z2 symmetries in Ising CFTs. And similarly, there's also the line N. And this line N, when it fused with itself, it can give you 2 possibilities. One is the identity lines and the other is the eta lines. And the fact that these lines can give you 2 possibilities is indicating that this is a line that is not invertible. So it's here eta has a property that if I fuse eta with eta itself, it just gives you identity. But when n fused with n, it doesn't give you just identity, it gives you some additional stuff. So in that sense, we call these things non-invertibles. Okay. And there's also a physical meaning behind these n lines, and these n lines are essentially related to the Kramers-Wiener dualities of the Ising models. So Ising model has a Kramers-Wiener duality that maps the high temperature phase to a low temperature phase. But then at the critical points, the Kramers-Wiener duality becomes the symmetries of the theory. It lifts the CFT invariant. And that symmetry is precisely described by this topological defect. So that's why we say it's also called the Kramers-Wiener duality line. Okay. So this is the first generalizations of symmetries to non-invertible symmetries using these topological lines. Because when we fuse these lines with itself, to be precise, this is the orientation and reversal of these lines. We don't get just identity, we get some additional stuff. So that's why it's called non-invertible symmetries. And another important data that enters into the formulation of topological lines is what's called F symbols. So it's essentially that if you fuse lines in different ways, they should give you the same answers, but then up to a non-trivial transformations. Okay, and this is what's called F symbols. So I just want to mention in passing that the mathematical structures underlying topological lines is what's called fusion categories. And this includes essentially the 2 data that I told you, the fusions of these topological lines and the F symbols. Okay. Okay, so these are the yes.
Sorry for the interruption, but Deepak just raising his hands.
Yeah, Ho-Tat, I have a quick question. I mean, maybe this is just a question of terminology. So Kramers-Wiener is the high temperature, low temperature duality, right?
Yes.
So, I mean, again, I'm not an expert in any of this. So if this is a stupid question, please don't mind, but shouldn't this be associated with the thermal operator? Like,
Oh,
isn't that what you said, the thermal operator?
yeah. So I'll come back to it when I describe the symmetry actions. But then whenever we have asymmetries, right? So we all agree that at the critical points, the Kramers-Wiener duality lifts the system invariant. So it should describe asymmetries. And then whenever we have asymmetries in two dimensions, it's captured by topological lines. So essentially, this topological line implements the symmetries. I'm going to explain what I mean by that. As you will see that the thermal operator actually charge under the symmetries. So this is consistent with the fact that if you apply the thermal operators on one side, if you do a Kramers-Wiener duality, it will change it to the other side. So that's why I map you to high temperature to low temperatures. I'll say a little bit more about this later.
Okay.
Yep. Okay. Thanks for the questions.
No, I mean, my question was that why is the Kramers-Wiener associated with the n lines and not with the eta lines?
You said eta. I heard you said epsilon. It's not related to eta line because eta line is implementing the Z2 symmetries of the Ising. It's just it flips all the spin up to down, so it has nothing to do with.
But eta, you identified eta as a thermal operator. That's why I'm asking.
Oh no! I'm not identifying them. So I'm not identified. They're not. They're not identified.
Okay.
Yeah.
Okay.
Yeah. It's just a coincidence that because these are Berliner lines, so the fusion of this the fusion of these lines has the same fusions as local operators, but they're not identified. You should not think of them identified.
Got it.
Good. Okay. So now let's talk about how topological line acts on local operators. Okay. So the way a topological line acts on a local operator is that you just imagine that you have a local operators and you surround your topological lines on it. And because it's topological, you can shrink it, then it will give you a new set of operators. So this is how you define the symmetry actions. And the reason why this defines the symmetry actions on operators is that by state operator correspondence, you can map the plane to cylinders. And when you map a plane to cylinders, then this operator is mapped to the states. And then when you apply a symmetry operators to the states, which is like surrounding this on the cylinders, is essentially like surrounding your line operators around local operators. And if you do this, it will map you to different states. So that's why the symmetry actions on the cylinders is mapped to the surrounding actions around local operators. So let's go back to Ising again. So we know that the Z2 symmetries shouldn't act on the thermal operators because the thermal operator is like made of roughly speaking the two spins, right? So that's why if I surround eta by epsilon, it just gives you epsilon. But then if I surround eta by the spin operators, it should give you a minus sign because it flipped the spin operators. So it agrees with well expected. And then the n line, importantly, as I already mentioned, that because it's a Kramers-Wiener duality, so it should map you from thermal operators to minus thermal operators, so that if you trigger a phase transitions, it will map you from high temperature phase to low temperature phase. Okay, so this is exactly what we have seen. But most interestingly is that if you surround this n line around the spin operators, then you'll find that you actually get 0. So that means that if I use the state operator correspondence, that means that this n line on the cylinders will annihilate the state that is due to sigmas. So because this operator annihilates the state, so that's why this is a non-invertible actions. So it's a non-invertible operators. So that's another way to see that this n line is associated with what's called non-invertible symmetries. Okay. But so this is something that I suspect if you already know about non-invertible symmetries, there's something that you might already know. But there's one thing I want to emphasize is that the reason why non-invertible symmetry is non-invertible is in some sense because these non-invertible symmetries are mapping you from the Hilbert space to a different Hilbert space. So what is this different Hilbert space I'm talking about? So this different Hilbert space is the following things. So if we have a topological defects, we can also let it end somewhere. For example, we can let it end on a local operator. And as a result, we'll get a sort of a combined objects, and this combined objects should be sort of some kind of non-local operators. Okay. So say I have a line A ends on the operator O. You can ask what is the physical meaning of this operator O. So you can do a state operator correspondence. So if I do a state operator correspondence, I map the plane again to cylinders. Then what we find is that this O actually becomes a state in what's called a twisted defect Hilbert space. Because you see, when I do time evolutions, I'm doing a radial time evolutions, right? So as I do time evolutions at every time slice, I see a presence of this topological defects. And what this topological defect does is that it's twisting the Hilbert space on cylinders to what's called twisted defect Hilbert space. So it changes boundary conditions on cylinders. So as a result, this operators O is mapped to a state in a completely different Hilbert space. It's mapped to a state in the presence of this defect, and that's why it's called twisted defect Hilbert space. And importantly, when I talk about topological defects, I always demand that it's just an operators that has physical meanings. If we want to bring it into it always has an associated twisted defect Hilbert space. So this actually put a very stringent constraints on what are the possible defects we can talk about. So now, with this sort of ideas of non-local operators and attached by topological defect lines, we can now ask the following questions. So let's consider that we have, again, the spin operators, but now we try to pass this n operators, this n line operators, the Kramers-Wiener duality line, through the spin operators and see what happens. So if we pass it through, this is essentially what we get, right? So these two configurations are topologically equivalent. But now we can try to fuse this part. But when we fuse this, we are fusing n with n. And then there are two possibilities that comes out. It comes out with identity or eta. So that means that there are two possible things we can obtain. One is that we just get an n lines, then with identity attached and another operators. Or we can get an n lines with eta attached and another operators. But in the case of identity, it turns out that there are no operators it can answer. So this is not possible, but this is actually possible. And as a result, what happens is that we are mapping the spin operators to what's called disorder operators. So this is an operator that are attached by the Z2 lines. And this is essentially a context of Kramers-Wiener dualities. It's mapping you from order operators made of the spin to a disorder operators made of the mu lines, made of this mu operators that are attached by the Z2 lines. So here we see that a very general phenomenon is that what is non-invertible symmetries? Non-invertible symmetries is non-invertible because it's generally mixing local operators to non-local operators, okay? So to capture these actions or this mixing of local to non-local operators, we introduced this, it's known before that we should introduce this concepts of what's called a tube algebras. So this is some concept that already exists in the literatures. So what is tube algebra? Tube algebra is essentially an operators that look like this. So it is an operator that map you from the A defect Hilbert space to a B defect Hilbert space, and then through this symmetry actions of C operators. And this operators, if you think about it by state operator correspondence, it's essentially operators that map you from A defect Hilbert space to B defect Hilbert space. And this is what's called lasso operators. It's like a lasso. And then you can shrink it, and then it will map you from A to B defect Hilbert space. And you can also compose them in the following ways. And then this defines an algebras. So that's why it's called tube algebras. And the reason why it's called tube algebra is because by state operator correspondence, it's just like a tube, right? It's mapping you, it's like acting on tube. So that's why it's called tube algebras. Okay, so now the important thing is that because non-invertible symmetry map between different defect Hilbert space, so when you think about the representation theories of non-invertible symmetries, you should think about it as combinations. You should think of the local and defect Hilbert space together. They form representations under these tube algebras. Instead of just thinking about local operators, you should think about the combinations as the representations under the tube algebras. Okay. So for example, the spin operators and the disorder operators, they actually form a two-dimensional representations under the tube algebras. And this is how the actions look like. Okay, so this is essentially everything I want to talk about topological defects. The important things I want to take away is that there's this idea of tube algebras. And as we'll see later, that this idea will inspire us to introduce this concept of chiral tube algebras. Okay, so is there any questions at this moment? about topological defects in tuple algebras? Good. Okay, so if there's no, then I'll move
I
on
have
to
one
talk about.
question.
Yes, please.
So the untwisted Hilbert space is a representation of the global symmetries of the theory we have. Is this also true of the twisted Hilbert spaces?
Sorry, can you say again? I didn't hear what you said.
So the ordinary Hilbert space that's not twisted is a representation of the global symmetries we have in the theory. Is this also
Mhm.
true of the twisted Hilbert space?
Generally, yeah, you can also think of it this way. So, I think the better way to think about this is that you should think about the combined things as a representation under these tuple algebras. But of course, you can always truncate your tuple algebras to say I always insist myself to consider something like AA and then with C inserted. So then, of course, then the truncated things will also form the representations under these things. Yeah. But then if you want to restore, essentially, if you want to restore unitarity, then you should consider these combined things. So the statement is that if you consider these combined things, the transformation is essentially unitary.
I see. Okay.
Yeah. Thanks for the questions. Okay, good. So now we're done with topological defects. Now we move on to sort of another branch of the talk that is about Chiral algebras, or mathematically it's also called vertex operator algebras. So I'll start with something that everyone knows if you have already think about 2D CFTs, and then we'll move up quickly. Okay, so the statement is that in 2D CFTs, Chiral algebras actually represent completely different notions of symmetries. So what is Chiral algebras? Chiral algebras are essentially a collection of chiral operators. So these are operators that only depend holomorphically on the z coordinates, and it doesn't have any anti-holomorphic dependence. So that means that these operators are annihilated by the partial bar. Okay, and one can show that this implies that these operators would necessarily have h bar equals to 0, but it can have non-trivial h. But then using modular T transformations, one can show that this actually puts the constraints on H, that H has to be integers in bosonic theories and half integers in fermionic theories. So there's this important spin quantizations conditions on these chiral operators. And then now with these chiral operators, we can also talk about the OPEs. We can bring two chiral operators together, and then it will again give us a set of chiral operators. So these chiral operators are closed under OPE themselves. So this is the essentially content of chiral algebras. So one important thing is that once you have a chiral operators, then you essentially have an infinite set of conserved quantities or infinite set of continuous symmetries. The reason is very simple. It's because if I have a operators that is chiral, we can multiply it to any power of z. And this will again define some operators that is holomorphic. Because this is holomorphic, then you can integrate it over some closed curve. Then this will define for you some operators. And these operators are line operators, importantly. And this line operators, importantly, is topological. It depends topologically on C because what's inside is a holomorphic functions. So that tells you that if you give me chiral operators, I can raise it to any powers, and then I can define topological operators. And because there's infinite possibilities of powers that I can insert it, so I basically get infinite continuous symmetries. Okay, and so the fact that this chiral operators give you infinite continuous symmetries is really the power of this chiral algebras. And one thing I want to emphasize is that you see that these chiral operators, if you integrate them, they give you a set of topological operators. But these topological operators, they are not topological defects. So even though they are topologicals, but then they don't have a well-defined defect Hilbert space associated with them. So that's why they are very different from topological defects. And I'm also going to emphasize another difference between this topological operators versus the one that we have seen before using topological defects. And of course, with this operators, we can also reconstruct the original local operators using the Laurent series. Okay, so this is something that we have seen in 2D CFTs. And so some quick examples is that the most classic chiral algebras is, of course, the Virasoro algebras built out of the stress tensors. So this is essentially, if you have an operator, a chiral operators with spin 2, then this will give you a stress tensors, and this OP is highly constrained. using by associativities, and then by integrating the stress tensor with some appropriate power of z, you can define this Ln operators, and then you can compute the algebra of Ln operators, and this is nothing but the Virasoro algebras in 2D CFTs. And one thing you can see is that you can ask what is the physical meaning of this Ln operators. So what this Ln operator does is that it's generating the reparametrization symmetries of or the conformal symmetries that map z to any functions, holomorphic function of z. Also, actually, meromorphic function of z. So essentially, Ln is mapping z to some z to the power. You're shifting z by z to some power n. So that's why you have an infinite set of symmetries, because the symmetry is parameterized by essentially holomorphic functions. Okay. So this is what happens when h equals to 2. But now you can ask what happens if I include the h equals to 1 operators. If you include the h equals to 1 operators, then you get a conserved currents. And then this gives you the famous Kasmudi algebras that exist in the WZW models. And, sorry, there's a typo. So you can also include, for example, in your fermionic theories, you can include three half currents. This is essentially the supercurrents. And if you add it to the Chiral algebras, it gives you the superconformal algebras. And there's something else you can do, is that you can add, for example, a spin 3 currents. And this essentially gives you what's called a W3 algebras. And this is something that I'm going to come back to later. And you can do the same thing. So you can just keep playing the same games by adding more and more higher spin currents. And this will give you some Wn algebras or some generalizations of Chiral algebras. So the study of Chiral algebras is essentially a study of this spin operators and their OPEs and so on and so forth. Okay.
Wait,
So
can I ask a question? I'm a bit confused about what spin tree current means. Like, it probably does not mean it's like a tree form, because in 2 dimensions we cannot have an object like that.
yeah, it's
What
not a tree
exactly do you
form.
mean by what exactly do you mean by a spin tree current?
Yeah, so in this case, it's just currents that is you shouldn't think about it as let me give me a second. Let me think about it. Good. So you should think about this as following. So rotations if you do rotations in 2D, it's U1, right? So you're essentially just consider
I see.
different.
The little group is the one. Okay.
Yeah, it's very different from higher dimensions, if that helps.
Yeah,
Yeah.
you're right. Yeah, okay.
Yeah.
Okay, by spin you mean something else. Okay, yeah. It's
That's
not
right. Yeah, so it doesn't change the indices. So for example, it doesn't mean that you have a lot of indices. Yeah, good. We'll see examples of this W algebra later. Okay, so one thing I want to emphasize, the importance, the difference between Chiral algebras and topological defects is there's also another important difference between Chiral algebra and topological defects. So this is also sort of the power of Chiral algebra, is that Chiral algebras actually allows us to solve 2D CFT exactly in many cases. So this includes, for example, minimal models, which is solved by using Virasoro algebras, and also WZW models, which is solved by Kasmudi algebras. And the reason why Chiral algebras allows us to solve 2D CFT exactly is because Chiral algebra is very, very different from topological defects in the following sense. They're actually spectrum generating symmetries. So there are symmetries that will generate a tower of states instead of just mapping you from a state to a state of the same conformal dimensions. So why am I saying that? The reason is following. So let's just focus on Virasoro algebras. So Virasoro algebras has this L0 operators, which is essentially the Hamiltonians in radial quantizations. So they are essentially Hamiltonians on the cylinders. But then if you look at the other generators of Ln, of Virasoro algebras, this Ln, they actually don't commute with L0s. So as a result, if you apply this Ln operators to the states, you can actually you can change the conformal dimensions. So in particular, you can start with the highest weight states, which are annihilated by Ln's with n greater than zeros. If you start applying L with the negative power of n, then you can start with the states and then get a states with higher conformal dimensions, and so on and so forth. So essentially, with this Ln operators, you can start with the states and start building a tower of states coming from this. And because of this, the spectrum is actually significantly reduced, because you can just group things into families. In principle, your CFT should have infinite spectrums, right? But then because you can group things into families, so in the nice case, what's called rational CFTs, a spectrum can be organized into finite number of E-reps under this Chiral algebras. And in that case, we can just solve the theory explicitly because of this significant cut down of the dimensionalities that we need to deal with. Okay, and so the fact that we can solve a lot of 2D CFTs using Chiral algebras is precisely because these Chiral algebras are spectrum generating symmetries. Okay, so this might sound something very weird, that why symmetries can be spectrum generating. So instead of the usual symmetries that we have seen that should commute with stress tensors and has commutes with Hamiltonians. The reason is that this is actually a very common thing. And this is because the symmetries that we're talking about, the Chiral algebras, they are space-time dependent symmetries. Remember that when we define the symmetries, we allow ourselves to add this space-time dependence, right? This z to some powers. And as a result, this turns this symmetry operators into what's called space-time symmetries, space-time dependent symmetries. And in fact, you see that the symmetries is parameterized by holomorphic functions, or a meromorphic function. So it has an explicit space-time dependence. So a classic example of space-time dependent symmetries is boost. Okay, so boost, if we try to build it out of stress tensors, it has explicit dependence on time and on x. And one can check that this operators is actually a conserved operators using the stress and using the conservation law of stress tensors. So this operator is the boost generator is actually conserved, but it doesn't mean that the boost generator commutes with Hamiltonians. The reason is that the conservation of boost operator is telling you that the total derivative of an operator with respect to time equals to 0. But total derivative actually receives two contributions. One is a partial derivative, and one is the commutations with Hamiltonians. And because it has explicit time dependence, so the partial derivative is actually non-zero. And this is nothing but the momentums, right? This is like integral of the momentum densities. So this gives you momentums. So so here we can see that we can have a conserved operators, even though this operator doesn't commute with Hamiltonians. And in fact, the way this operator doesn't commute with Hamiltonians is precisely what we expected from boost. So if we commute this, if we try to commute boost with Hamiltonians, what we find is essentially the momentum operators. This is because a boost will miss Hamiltonians with momentums, right? And this is precisely what we have seen. So I just want to emphasize that the fact that the symmetry operators doesn't commute with Hamiltonians is nothing mysterious. It's just because this is a space-time dependent symmetries. And in fact, in the case of boost, this nicely gives us the correct symmetry transformations. And this is also a characteristic of this Chiral algebras. That's why it's spectrum generating. Okay, good. So now let me summarize what I have discussed so far. So far, I'm just reviewing things that has been known, but then I also want to sort of put this two concepts in parallels and then try to compare them. So in both cases, both topological defects and Chiral algebras, they define some topological operators in our theories. And in the case of Chiral algebras, it's always associated with some continuous, infinite continuous symmetries. And in particular, it's the space-time dependent symmetries. But in the case of topological defects, it can describe both discrete symmetries and continuous symmetries. So this is one difference between the two. And the second important difference between the two is that topological defects always have this notions of defect Hilbert space. And this puts a very strong constraints on the possible topological defects that we can have. While the symmetry operators that we built from Chiral algebras, they're just topological operators. They don't need to have a well-defined defect Hilbert space interpretations. And lastly, because Chiral algebras, the symmetry operators associated with Chiral algebras has explicit space-time dependence, so they're actually not spectrum preserving, they actually generate spectrums, and they give you a tower of states. And this is very different from topological defects. So in case of topological defects, it doesn't change the conformal dimensions, okay? So this is a difference between the two important concepts. But still, they define topological operators, so they define some symmetries. Okay, so now I'm after more than...
Can I ask another question?
Yes, please.
So we can understand topological defects from the SIMTFT. Can we also understand the chiral algebra from a SIMTFT like construction?
That's a very good question. To be honest, I don't know. So I think it should be connected with this Chern-Simons Wess-Zumino the WZW model sort of correspondence. But then
Like the
on the other
graph
hand,
written. Yeah.
it's more like transaminase, and then it's like transaminase, and then you need to pick some holomorphic boundary conditions. Then maybe you can get then you usually get Chiral algebras on the boundaries. But then it's very different from the SimTFT pictures, because SimTFTs there we always pick some gap boundary conditions. So yeah, that's a good question, and I don't know the answer actually. Yeah, I don't know the clear
Okay.
answer. Yeah.
Okay.
Thanks. And yeah. Okay. Good. Okay. So now I spent more than half an hour talking about things that should be known, but then I hope this set a stage for what I'm going to talk next. And now I would like to get to sort of the questions that we're trying to answer in today's talk, and then sort of the reason why we introduced this Chiral algebras. So there are three things we would like to ask. One thing we would like to ask is that, okay, we have this notion of defect Hilbert space. So usually we talk about how the local operators, local spectrums are organized into representations under Chiral algebras. But what about defect Hilbert space? A defect Hilbert space, can we organize defect Hilbert space into Chiral algebras representations? So this is sort of a side comment, is that we know that topological defects necessarily commute with stress tensors, so that they always preserve Virasoro algebras. So we can always organize the spectrum into Virasoro representations. But what about extended Chiral algebras? Like, can topological defects always preserve extended Chiral algebras, or what do they interact with the extended Chiral algebras? So that's the first question. The second question is that we can also ask what happens to Chiral algebras if we try to gauge the symmetries. So let's say we gauge some symmetries, or we try to do some overfolds. What happens to Chiral algebras? So one thing to notice is that gauging usually just reshuffle operators. It doesn't lose any information, because when you gauge, you can always gauge back. So one can ask, if you gauge the symmetries, does the gauge theories know about the Chiral algebras, or how does it sort of encode this information of Chiral algebras that was there before? And the third question we'd like to ask is probably also the most interesting questions, is that often the case as we'll see that by gaugings, we'll turn a currents into a non-local current, which are currents attached by some topological lines. Then one can ask, can we build the Chiral algebras using non-local currents? And this is actually a very important point, because we know that a local current always have integer spins or half integer spins, depending on its bosonic theories or fermionic theories. But if we consider a non-local current, then we can consider some currents which have some fractional spins. And this, if we can include non-local currents into Chiral algebras, then we can significantly enhance the possibility of Chiral algebras. And the hope is that by enhancing this possibility of Chiral algebras, it allows us to solve more CFTs, or to have access to more CFTs. And in fact, this non-local currents or Chiral algebras from non-local currents in some sense already appeared in the literatures. So classic example of this is what's called parafermions. So this is an example of it's an operators that are attached by some Z3 lines. And this operator has a fractional spins, which is given by 2/3. Okay. So, but as I'm going to explain that using Chiral tube algebras, we actually can make this study of non-local currents more systematic. And in fact, non-local currents has been appears in various studies already in recent years. So in particular, they has been used to study continuous non-invertible symmetries. And I think there was talk by Yunqing. They talk about the recent papers that use non-local currents to build continuous non-invertible symmetries. And then they're also been used recently by these very nice papers that try to use try to build some non-local charges that can preserve under RG flows. So this and it also has interesting connections with interoperabilities. So this is also another use of non-local currents. And as we'll see in today's talk, that we'll use this non-local currents to build some Chiral algebras. Okay, so these are the questions that I would like to ask. Is there any questions about the questions? This is essentially the most important part of the talk, that what are the things we're trying to address? Okay, so if there's no questions, let me know, just essentially tells you that what is this Chiral algebras. So this Chiral algebras is the things that naturally emerges if we're trying to answer these questions. And the structure of this Chiral algebras is very similar to, much similar to tube algebras. So they are something, again, like this kind of lasso operators. So there are operators that map you from A defect Hilbert space to B defect Hilbert space. So what's sitting vertically are always topological defects. So I use red operators to label topological defects. And what's sitting horizontally now is not a topological operator, so topological defect. It is really the modes of the chiral algebras. So this is those operators, those integrals of the chiral operators to some power of z. Okay. So this is the fundamental objects that build the chiral tube algebras. And you can also compose them similar to how you compose things in chiral algebras. No, sorry, in tube algebras. So you see that this is very much similar to tube algebras in the sense that this is an operator that map you between different defect Hilbert space. It's also similar to chiral algebras because the generators, the symmetry the operator that implements the symmetries is really some mode of the chiral operators. So that's why we call it a chiral tube algebras. Okay, so now I'd like to explain how this chiral algebras, tube algebras can help us to answer all the questions that we raised before. So the first questions we ask is that how does chiral algebra act on different defect Hilbert space? So the simplest, so first of all, I want to consider extended chiral algebras, meaning that we don't just have reversal algebras, we have something additional. And the case I want to consider is the case when we include a spin-free current. So this is what's called the W3 algebras. I'm not writing down the details of the W3 algebras. It's a bit complicated, but one thing I would like to mention is that if you look at the commutators of L0 and the mode expansions of Wn, you'll see that this Wn actually change the eigenvalues of L0s. So that means that by acting Wn, you can map you can change the conformal dimensions from let's say h to h plus n or h minus n to in this case. But also it will map you from one Virasoro primaries to another Virasoro primaries. So that means that in W3 algebras, you can decompose things into various Virasoro primaries, and then they will naturally be connected by this Wn operators. Okay. And you can also consider the commutators of Wn's. And one thing that's kind of very unusual about W3 algebra is that when you fuse two Wn operators, you get some operators that is quadratic in Ln. And so this is very different from Virasoro algebras. So Virasoro algebra is linear algebras in the sense that if you take commutators of two Ln's, you just get Ln. But in this case, if you take commutators with Wn's, you actually get something quadratic in Ln's. So that's why W3 algebra is a nonlinear algebras, and that's also why this is something that's very different from Virasoro, and this that's why people are still working on this. It's something that this nonlinearities allows us to open many possibilities, and that's why Wn algebra is still a very active subject of study. Okay, so I'm going to consider this W3 algebras, and then I'm also going to consider the simplest models that have W3 algebras. This is what's called the three-state parts CFTs. So this is a CFT at central charge 4/5, and this is also minimal models, and so that's why this only have finite number of Virasoro primaries, and this makes our study much easier. Okay, so now let's talk about this three-state parts CFTs. So because we're studying theory at central charge 4/5, so we can ask what are the possible Virasoro modules or Virasoro representations at this central charge. So it turns out that there are in total 10 possible Virasoro modules, and they are labeled by their corresponding highest weight states, the dimension of their highest weight states. And it turns out that the first 6, they form representations under W3 algebras. And so, for example, these two Virasoro representation actually combine into one W3 representations, because starting with this, you can add W-3s to get these operators, and then they combine into one representation. And similarly, start with this, you can add W-1 to get to these operators, and they give you again a W3 modules. And this, they independently give you a W3 modules. But importantly, inside W3 modules, you also have this W0 operators. And then it turns out that you can have two distinct W3 representations, which have the same H for the highest weight states, but then they are distinguished by the W0 eigenvalues. So one of them has positive W0 eigenvalues, the other has negative W0 eigenvalues. So in total, there are actually 6 W3 modules. So this split into 2, and this splits into 2. Okay, so in total there are 6 W3 modules. And indeed, in the case of three-state parts, we can organize the spectrums into W3 modules. We see that there are modules coming from identities. Module comes from 2/5. Module comes from 2/3, 1/15, and 1/15. So all of the states that appears in three-state pods, they happens to appears just coming from this Virasora representations. So you can always organize them into W3 algebras, W3 representations. These are not W3 representations, and indeed this doesn't appear in three-state pods. And notice that in the spectrum of three-state pods, we have this operators and this operators. So there are conformal primaries, which are chirals and anti-chirals. And they are precisely the generators of the W3 algebras. So they are precisely the W operators that I mentioned here. So these are the spin 3 chiral operators and spin 3 anti-chiral operators. Okay, so they are the generators of the W3 algebras. Okay, so this is a local spectrums of three-state pods. So we see that nicely organized into W3 modules. We can now ask what happens to defect Hilbert spaces. Can we also organize spectrums according to W3 algebras? So in three-state pods, it turns out that there's S3 symmetries we can talk about. And this S3 symmetries consists of some Z3 symmetries generated by eta lines and some charge conjugation symmetry generated by the C lines. And there's also some Kremers-Wiener lines, which is a non-invertible lines. If you fuse it with itself, it gives you identity eta and eta bar. Eta bar is essentially eta squared. Okay. So now we can ask, how does this topological lines, for example, eta C and N, interacts with the chiral operators or the anti-chiral operators? So it turns out that eta acts trivially on W and W bar. C flip them by signs, and then N actually acts not trivially on W's, but acts trivially on W bar. And this has important consequences. So the consequences is the following. So because eta doesn't act on W's, so they actually preserve the W3 algebras. And as a result, the eta Hilbert space, we see that they can all organize into W3 representations. So these are all representations of W3 algebras. As you see that these numbers are always the numbers that appears here. Okay. And so we can encode the symmetry actions of this W generators by the following tube algebras. So essentially, it's a loss operators that map you from eta to etas with the horizontal operators given by Wn, OLN. Okay, so this is the generators of the Wn algebras in the eta defect Hilbert space. Good. But now let's talk about the other operators. What about the defect Hilbert space of C? C actually interact non-trivially with the W operators and W bar. So naively, you would say that C only preserves Virasora algebras. But this is actually too quick because we can actually still talk about the actions of W3 algebras in Virasora algebras. Sorry, in this C defect Hilbert space. But there's the subtleties. The subtlety is the following. So now imagine that we have we're talking about the actions on a defect on the local operators that are attached by C. Then if we bring this W operators around, it actually will be acted upon by C by minus sign. So that means that this W operator actually is not periodic when we bring around C defect operators. It's actually anti-periodic. So it has non-trivial monogemies. And this implies that we can still talk about, we can still expand W's into mode, but the mode expansions now would not be integer mode expansions. It's actually half integer mode expansions. Okay, so this is odd mode expansions. And I'll use R to denote odd mode expansions and use N to denote even mode expansions. So we can encode this twist of mode expansions by this lasso operators. So it again maps you from C defect Hilbert space to C defect Hilbert space. But now the symmetry operators that acts horizontally is an operators is a mode of W's, but then with odd mode numbers. And it turns out that WR operators, they actually form the same algebra as Wn. So they essentially take the same form, except that all of the n has to be shifted to R. Okay, all of the n has to take half integer. And so we call these things W3 prime algebras. This is essentially a twist of the W3 algebra. So it's a twisted W3 prime algebras. And you can ask, what is the W3 prime modules? What is the representation of this W3 prime algebras? And it turns out that the things that was excluded before, so we know that these are W3 modules. These things that were excluded before, they turns out to be a W3 prime algebras, the W3 prime modules. Right. So what happens is that there are 4 Virasoro primaries, and it turns out the 1/8 and the 13/8, they're actually combined into one W3 prime modules. They're connected by the action of W minus 3/2. And 114 and 21/40 is also connected by a W of minus 1/2. So this is a W3 prime modules, and this is a W3 prime modules. Okay. And indeed, if you look at the defect Hilbert space of C, they are all organized according to this W3 prime modules. So this tells us that we can indeed organize the spectrums of the defect Hilbert space into Chiral algebras, but now the Chiral algebra actually is twisted. So it's a twisted Chiral algebras. So in summaries, the Chiral algebras of 3-state pods includes all these things. So we see that in identity and eta defect Hilbert space, we just use integer mode expansions. In the C defect Hilbert space, we need to use half integer mode expansions. And in the N defect Hilbert space, for the Chiral part, we use odd mode expansions, but for the anti-Chiral parts, we actually use integer mode expansions because N actually acts differently on W and W bar. Okay, and then we can organize the spectrums of defect Hilbert space generally into the under this twisted Chiral algebras. So this is this answer the first questions. So generally, defect doesn't break Chiral algebras; it just twists the algebras, and then the defect Hilbert space just organized under this twisted Chiral algebras. So this is the first questions. So let me move on to the second questions that I would like to ask. Is that what happened to Chiral algebras if we gauge the symmetries? Okay, so this example actually worked very nicely because we can, if we start with the 3-state pods, we can gauge the Z2 symmetry generated by the charge aggregations. It gives us another CFTs, which is what's called a tetracritical Ising. Okay. So one thing to notice importantly is that if you gauge the Z2 symmetries, you actually get a dual Z2 symmetries. And that dual Z2 symmetries, you can think of it as generated by the Z2 Wilson lines of the Z2 gauge fields that you couple to the CFTs. And because it's a Z2 Wilson lines, it's actually topological because there's no field strength associated with Z2 symmetries. So that's why it generates the symmetries. And I'll call this dual symmetries Z2 tilde symmetries, okay? And similarly, you can also start with tetracriticals and gauge the Z2 tilde symmetries and come back. So that means that 3-state pods and tetracriticals, that in some sense they share they contain the same informations because you can always recover one from the others. But what gauging does is really reshuffling these informations and place these informations in a different way. So for example, consider this case. In a 3-state pod CFTs, you can organize the spectrums into whether they are charged under the Z2 symmetries or not. And then you can also organize them according to whether they are coming from the local Hilbert space or the Z2 defect Hilbert space. So this is how I list the operators. I didn't list all the operators, I just list some of them. And as you can see that these operators, they form W3 algebras, and this operator W3 representation, and this operator, they form a W3 representations. But what gauging does is that it reshuffle these informations. So in particular, it mapped this to here and this to here, okay? So in this case, I'm organizing the spectrums according to the Z2 tilde symmetries generated by this C tildes. And then we see that what happens is that the operators that are charged on the Z2 symmetries, they become non-local operators. Because they're charged on the symmetries, they have to be attached by Wilson lines. So they now becomes operators in the defect Hilbert space. On the other hand, operators that are living inside the twisted Hilbert space attached by C, they actually are liberated if they are charge neutral. They are liberated becomes the local operators. This is because after gauging, the topological lines that attached to becomes transparent, right? Because it doesn't act on anything, so it becomes transparent, and that's why they becomes a local operators. So what we have seen is that after gauging, the operators' contents are actually reshuffled. Some operators becomes non-local, and some non-local operators becomes local. And in particular, the W operators, which is the local operators that generates the W3 algebras, actually becomes the non-local operators after the game, okay, after gauging. So that's why it
Can I ask
connected to the
something
about
about
yes,
this
please.
part? Does this care about whether the group we are gauging is non-abelian or not? Because when we gauge a non-abelian group, we may get like non-invertible symmetries. Does this change anything about your conclusions? Or
That's a good thing. So that's a good question. So if you gauge a non-abelian symmetries, what happens is that you can again organize things into the dual symmetries, which in this case is what called the Rebji symmetries, and then you can organize this into a Chiral tube algebras and organize this into tube algebra representation and things like that. And
okay, so it doesn't care about whether it's non-abelian or
yeah,
not.
the fact that you can recover informations, the two CFT contain same informations, doesn't care about whether it's non-abelian or not.
Okay.
But then the way this operators are shuffled or combined are more complicated.
I see.
That's a point. Yeah.
Okay, thanks.
Okay, so now actually I think I'm running out of time. So do you think I can get 10 more minutes or I should just stop right now?
Yeah, actually, we don't have any time limitation, or you can just
Okay.
go away. Yeah.
Good. Thanks. So yeah, so now we see that in this case we actually encounter non-local operators, right? So now this actually turns us into the third questions that we would like to ask is that if we want to understand Chiral algebra algebra gauging, we need to understand the following questions. Can we build the Chiral algebras from non-local Chiral operators? So in particular, we are encountering this non-local Chiral operators. Can we build a Chiral algebra out of it? So this is a question we'd like to ask. So if we want to build a Chiral algebra out of it, we need to find a way to absorb this lines it is attached to, this C tilde lines. And this, in fact, can be done using the projectors. So we can build a projectors out of these C tilde lines by combining the identity with C tildes. We can build some projectors. And so now with these projectors, what we do is that we can push this non-local currents onto the projectors. And when we push this non-local current to the projector, we get something like this. We get something like this, but then with the currents attached to it. So the currents now actually live freely on the projectors. It can move around from projectors. So the currents actually becomes a local current, become some local currents that live on these projectors. Okay. And if I push these things on this thing, what happens is that we see that it becomes something. If we expand it into components, we get something like this and something like this. So if I push these things on the projectors, I essentially get a linear of two kind of operators that are in different ways. Okay. And the use of projector is because if I take this very particular linear combinations, that this operator, this Chiral operators, actually have a well-defined monodromy. Move it around, the circles. So it has a positive. It has a trivial monodromies living on P plus, and they have non-trivial monodromy of -1 phase when it's living on P minus. Okay, so that this operator has a periodic on P plus and anti-periodic on P minus, and then that tells us that we can again expand these operators into. And so we now have the following Chiral tube algebra or generators or the following lasso operators. So this is an operator that map you from a trivial Hilbert space to a C tilde Hilbert space, and then there's a projectors that acting on it, and depending on projectors, we'll expand the mode into positive, into integers mode or half integer modes. So you can similarly do the things by pushing these operators in the other ways. Then you will get a different set of Chiral lasso operators. So this is the complete set of lasso operators that involve C tilde, defect Hilbert space, and identity Hilbert space. So what you have seen here is that using these projectors and this pushing of currents to the projectors, we can build a set of lasso operators. But these lasso operators are very different from the one that we have seen before. This is lasso operators that map you between local Hilbert space and defect Hilbert space of C tilde. And the mode expansions actually depends on the charge of the symmetries that you act on. Okay, and it turns out that these operators they are closed under themselves, and they form the W3 algebras. They form an algebra that is isomorphic to W3, and these operators they're closed under themselves. They form an algebra that is isomorphic to W3 prime. But these operators and these operators they don't talk with each other because of this projector business. Okay, so they actually don't talk with each other. Okay, so now that tells you that you can organize again the Hilbert space into representation on the W3 algebras and representations on the W3 prime algebras. But now you need to be careful is that when you start with the local operators, if you apply the W3 generators, it might map you to non-local operators. So for example, let's start with identity operators. If we start with identity operators, we can apply this lasso operators, right? Because this is charge neutral and under the C tilde symmetries. And then we can apply this lasso operators and get the operators that are attached by C tildes. So indeed, if we start with these operators, if we apply the W minus 3, we get these operators. And this is again an operator that is charge neutral under C tilde, but this is operator now living inside a defect Hilbert space. And you can now apply to W minus 3 bar, and then you can go from this operator to this operators and get this Y operators. So these operators, they actually form a W3 representations. And these operators, because they are charged under Z2 tilde symmetries, they actually form a representation under this lasso operators. And they are actually representations of W3 prime algebras. So what we have learned here is that gauging actually generally turns Chiral algebras that acts on local operators into that are generated by local currents into Chiral tuple algebras, which are generated by non-local currents. And what this Chiral tuple algebra does is that it generally maps you between a defect Hilbert space and a local Hilbert space. So it's an operator. The lasso operator actually mixes different Hilbert spaces. Okay. So let me skip this part now. Okay, actually, let me just say something very quickly. So far I have just been talking about defect Hilbert space involving local Hilbert space and C tilde. We can now ask what about the other defect Hilbert spaces. So it's related to a question that was asked. So if you start with the Z3 lines in 3-state pods, it actually doesn't commute with the Z2 symmetries, the Z2 charge aggregation symmetry we gauged. So that means that after gauging, it actually becomes a non-invertible lines. And this non-invertible lines we denote by M has a property that it absorbs C tilde. Okay, so it actually absorbs C tildes. And as a result, you can actually build a Chiral tuple algebra again. But this Chiral tuple algebra now is actually different from this one. It's actually closer to the one that we have seen before. So this is a Chiral tuple algebra where you again map you from just M defect Hilbert space back to M defect Hilbert space. It doesn't mix defect Hilbert spaces. But in this defect Hilbert spaces, you need to introduce projectors. And then depending on projectors, your W operators will expand into either integer modes or half integer modes. So indeed, if you look at the M defect Hilbert space, it has a bunch of operators. And then if you split them into operators that are charge neutral under C tilde and charge odd under C tilde, you see that they actually form W3 representations. So these are all W3 representations or W3 prime representations. So this is consistent with the lasso operators that I just constructed. Okay, so this is just to give you a flavor of what happens to the Chiral tuple algebras after gaugings. So you can also get some Chiral tuple algebras that just map you inside same defect Hilbert spaces. So there are a lot of examples that we work out, but I didn't get a chance to discuss is that you can consider, for example, Kasmoudi algebras, and then you gauge it. So for example, if you start with SU2 level 1, if you gauge it, you get to some compact boson theories. And then in that case, you also have some Chiral tuple algebras built out of SU2, non-local SU2 currents. And then you can also consider superconformal algebras, which is a fermionic theories and what happens under bosonizations. So for example, tricritical Ising models is a bosonization of a superconformal field theories. And in that case, you also have some non-local supercurrents and you can use it build some super conformal tuple algebras. So this is some other examples that we also work out. So lastly, I want to give you sort of a taste of where we are going forward. So far, I have been only telling you examples that are coming from just gaugings. So all of the non-local currents I talk about are just coming from gaugings. So as a result, the algebra that we have seen, even though they become some Chiral tuple algebras attached that map you between different defect Hilbert spaces, but this algebra they formed, this algebras they're actually isomorphic to the local Chiral algebras that we have seen already before gaugings. So one can ask is that whether they are intrinsically non-local Chiral algebras. So these are Chiral algebras that built by some non-local currents that doesn't come from something that we have seen before, like doesn't come from some Chiral algebras, local Chiral algebras built from local Chiral operators. So indeed, this has been seen before. This is precisely a pair of fermions. So because all of the local Chiral operators always have integer spins or half-integer spins, so if we find a currents which have fractional spins, and if we are able to build some Chiral algebras out of these currents, then this is necessarily an intrinsically non-local Chiral algebras. So for example, parafermions is such examples. So parafermions actually already exist in three-state pods. So in three-state pods, if you look at the eta defect Hilbert space, let me show you the eta defect Hilbert space, we find that there are this non-local Chiral operators, and their spin is 2/3. So these are precisely parafermions, and they are because they have fractional currents. So if we can build the Chiral algebras out of parafermions, then they are necessarily intrinsically non-local Chiral algebras. And in fact, that has been done before, but at that time people didn't know about topological defects, and this has been super helpful in solving various CFTs. So they form what's called a parafermion Chiral algebras. So now instead of telling you about this parafermion Chiral algebras, I would like to tell you something that already exists in Ising CFTs. So in Ising CFTs, there's also this intrinsically non-local Chiral algebras, and the way to see that is the following. So this is the complete operator spectrums in Ising CFTs. We see that in the Z2 defect Hilbert space, there are non-local Chiral operators. They are nothing but Lamar fermions. So there are Chiral operators and anti-Chiral operators. But interestingly, if you look at the defect Hilbert space of the Kramers-Werner duality lines, you also find some Chiral operators. And this Chiral operators has dimension 116. Okay? And we can ask whether we can add this Chiral operators into Chiral algebras and build some Chiral tuple algebras, and what is the representations of this Chiral tuple algebras. So let me skip this part about the fermions. So you can use fermions to build some Chiral tuple algebras. I'll just be very brief. That you can build some Lasso operators that map you between local Hilbert space to defect Hilbert space, to the Z2 defect Hilbert space. You can also build some operators that map between the n defect Hilbert space. And and as a result, you can organize the spectrums into representations under the NS sectors of NS sector fermionic algebras, under Ramon sector fermionic algebras. And it turns out that if you look at the spectrums, they're precisely organized into representations under this NS sector fermionic algebras or Ramon sector algebras. So for example, these operators, they form representations under the NS sector algebras. And these operators, they are all charge neutrals. And so as a result, you can extend by this Lasso operators, and then if you add this by this Lasso operators, it maps it from here to here. And this operator now has charge under the Z2 symmetries, and now you can apply this operators, and then this will map you back. Sorry, you can apply this operators. They will map you back from here to here. Okay. And similarly, these operators are charged under the Z2 symmetries. So as a result, you can apply the Ramon sector Lasso operators, and this will map you between the operators, the spin operators, or the order operators to disorder operators. But now they are in different defect Hilbert space. Okay, so this is what happens if we want to build a Chiral tuple algebras from fermions. we can also do the same things if we want to build a algebras, a Chiral-2 algebras from this S operators, which have spin 116. So the way we do it is very similar to what we did before. We start with the projectors, but these projectors now involve the N operators and the eta operators, and this is the projectors that we built. So this projector has the following properties. You see, if I fuse these projectors with N, I actually, first of all, if I fuse with N, I'll find that it gives you the same projectors, but then with plus or minus sign. You can check this using this fusion rules. Okay. So that means that if I push the S operators that are attached by N lines to these projectors, the N lines will be absorbed by these projectors. And if we expand it into explicit components, this is the operators that we are thinking about. So this is this linear combinations of operators. And it turns out that the monodromy of this S depends on the projectors. So if the projector has positive sign, then it's periodic. If it has minus signs, it's anti-periodic. So as a result, you can build this Lasso operators, and then the mode actually depends on which mode expansions. Which projectors you're using. So here we see that we have a set of Lasso operators that map you from local Hilbert space to n-defect Hilbert space and vice versa. We also have a set of Lasso operators that map you from eta defect Hilbert space to n-defect Hilbert space. And using these Lasso operators, we can now organize the spectrums again into representations. So for example, the identity operators will be annihilated by P minus, but it will not be annihilated by P plus. So as a result, we can apply the P plus operators to our identity operators. And what it does is that it will map you from these operators to the defect Hilbert space operators. And now with these operators, we can now apply the anti-Chiral operators. It will map you from either this one using this or this one using this. Okay. So what we have seen is that we can organize again the spectrums into representations under this Chiral-2 algebras built from S operators. And what color in red are in the same representations, what color in green are in the same representations, what color in blues are also in the same representations. This operators form its own representations. So one thing to notice is that if you combine the fermionic Chiral-2 algebras with this S Chiral-2 algebras, you can see that everything that you know in Ising CFTs can all be generated by just the identity operators. You start with identity operators, you can apply this Lasso operators one by one, then this allows you to obtain all the other states. Okay, this is actually the features of minimal models. Okay, so let me conclude now. So as we have seen that even in the simplest 2D CFT, the Ising CFTs, there exists this intrinsic non-local Chiral algebras. And we can use this intrinsic non-local Chiral algebras to organize the spectrums involving both the local Hilbert space and defect Hilbert space into representations under this Chiral-2 algebras. And this really suggests that this might be some new tools that can help us understand or study 2D CFTs better. Because this intrinsically non-local Chiral algebras greatly enhance the possibilities of Chiral-2 algebras that has been studied before. So let me summarize what we have discussed in today's talk. So what we have discussed is that by combining two very important notions of symmetries in 2D CFTs, namely topological defects and chiral currents, or even non-local chiral currents, we can obtain this combined objects called Chiral-2 algebras. And the Chiral-2 algebras are generated by these Lasso operators, which generally map you from one defect Hilbert space to the other defect Hilbert space of the topological defects. But then the symmetry actions are implemented by the mode of these chiral operators. And they form some algebras. You can compute their commutation relations and so on and so forth. And so this is showing you that there's this general universal structures, symmetry structures that exist in 2D CFTs. So one, of course, a very natural question one would ask is that can we find find applications of this symmetry structures, can we use this non-local occurrence to constrain or even solve some CFTs? And another interesting direction is that it turns out that Chiral algebra is something that not just exists in 2 dimensions, it also exists in 4 dimensions. So in 4 dimensions, if you consider some n equals to 2 supersymmetric theories, you can take some operators inside the theories and put it on a plane, and it turns out that they depend only holomorphically on that plane. And so that means that there's actually a correspondence between a Chiral algebras and a set of operators in 4D n equals to 2 supersymmetric theories. So one can ask whether this Chiral tuple algebras also has some use or appearance in the 4-dimensional supersymmetric theories. So this is some future directions that will be interesting to think about. And that's everything I want to say. Yeah, thanks. Yeah, sorry for running over time.
So actually, thank you for the great talk. We can take a couple of questions if you have.
I have one question. First of all, thanks for the great talk. When you were talking about the first question, I was going to ask this, but my connection was not stable, so I missed it. You were talking about how the defect Hilbert space is a representation of the twisted algebra, W algebra. This is essentially like a version of Kalan-Rubakov effect, right? Like the fermion monopole scattering problem has a similar aspect that's going on. Is this like related?
Well, in what sense is the same as Karan-Lubokov? What do you have in mind?
Like if we scatter a fermion out of a monopole, the quantum numbers change in such a way that, like, just as you have a n modes, integer modes turning into half integer modes here, when you look at the twisted defect space, twisted Hilbert space, when you look at the scattering of a fermion out of a monopole, the spins kind of change by half.
Oh, okay.
This is like
So,
essentially the same effect, right?
you're talking about the spin. You're talking. Oh yeah. Sorry, you're talking about the Lorentz spin, not a symmetry charge.
Not the Lorentz spin, maybe. I mean, not exactly, but in terms of spirit, these are like essentially the same effects, right?
They are. I wouldn't say they are the same effect. So what you have in mind is actually closer to this effect. Let me say quickly. So what you have in mind is something like this: that your symmetry actions in a local Hilbert space acts as a linear representations. Okay, but then they can act projectively in a defect Hilbert space. I think that's more closer to what you have in mind, or more closer to what happens in Kalan-Rubakov effect. So this actually happens in, for example, this case. So think about a Z2 symmetries. A Z2 symmetries in Ising actually acts just as plus or minus sign in a local operators, right? But then in the N operators, in the N defect operators, it can actually act as a plus I or minus I. And the reason why it can act as, so in some sense, it acts projectively. So there's this fractionalizations happening. And the reason why there's this fractionalization happening is because, roughly speaking, if you fuse this the eta operators with eta operators in n defect Hilbert space, you need to use some f move or this f symbols, and then as a result, eta squared is actually -1, and that's why you have this fractionalization. So. I think the twisting is a little bit different from that case. The twisting is more
I
like
see.
it acts on a Chiral operators. Yeah.
Okay. Now it's more clear. Okay.
Yeah. So yeah, in fact, this factorization is very important because you see, now I'm actually using different projectors. I'm using plus side and minus side projectors instead of plus and minus projectors. Yeah.
Okay.
Thanks for the question.
Thanks again for the nice talk.
Thanks.
If there are no other questions, we can just stop recording. Other questions? Okay, there seems to be not. I'm stopped recording. Thank you again for the great talk.
Yeah, thanks. Thanks for staying over. Yeah, it's pretty late now, right? I don't know what time is it at your time. Yeah.